So hello everyone, welcome back to MindMatrix. I hope you are doing well. I'm Sachin Tanwar. Today we'll be, proceeding with the further session on probability, which is going to be conditional probability. Okay, so before proceeding further, I would like to thank you all because I was getting a number of messages on Telegram, students who have joined our Telegram group, how our sessions are helping them. They are able to, solve good questions. And, like if I talk about other, subjects for GATE, so over there probability is like at very lower level, which is being asked in the GATE exam. So over here we can expect some good number of questions, and I have given you good questions. You have practiced that. Okay, so I was getting the messages. Apart from that, like we started from scratch and now we are having 450 subscribers nearly. Okay, so like I'm very thankful to you guys, and I guess like by the by our new year we'll be completing 500 subscribers as well. So keep sharing, guys. Thank you for all this. I'm overwhelmed with the response because I was not expecting this much of response. The views are also increasing day by day. So again, thanks a lot. Okay. So I'll request you now that if you are getting, if you're learning, if you are, feeling that, okay, you have got the value, do like, comment your feeling, and then proceed with the sessions. Okay. And make sure you're sharing it with your friends as well. So let's proceed further. So yeah, this is my introduction. I hope you all are aware by now. Whosoever is like following me. So I'm upcoming data scientist at Louis, India, and right now I'm pursuing M.Tech AI at IISc Bangalore. Teaching experience you can see and achievement, and yeah, I have gathered quite a good number of views on YouTube as well. So let's come to the point, the agenda of today. Okay, so if I talk about today, so we'll be discussing conditional probability. In the last few sessions we have already seen, like the basics of probability and the questions based on that. So today in the session we will also be including the question which was there in sample paper, which is given by IISc. Okay, so we'll be solving that as well, and we have got some examples as well for you to solve. Okay, so this is going to be the agenda. You can see motivation, definition, important points, examples, and questions. So let's proceed further with the motivation. So yeah, here is a big theory I have mentioned over here. The reason being because I'll be solving this problem as well. Okay, so let's just go through this. What exactly is written over here? So consider a state lottery game in which 6 numbers are drawn without replacement from a bin. Okay, let me just give you a brief idea. So let's suppose there is a lottery stuff, lottery, state lottery, which is there. Okay, and every individual buys a lottery. So there are 6 numbers with replacement from 1 to 36 numbers which a person draws. Okay, then he goes back to home, and then there is a result announcement day on which the lottery owner people they announce that what are the lucky numbers. Okay, they announce these 6 numbers, and for whichever person those 6 number matches, they win that lottery. For whichever person, whosoever those 6 number matches, that particular person wins the lottery. Now the point is, if I tell you that, okay, what is the probability of winning a lottery? So over here you will say it's quite less. Okay, it would be less for sure. But if I say that, okay, let's suppose that one of you was sitting and he just turned on the TV to just check the result, what is being announced, and then you suddenly listen that, okay, there is one of the number you already have which is being announced, and when they are announcing the further numbers, suddenly what happens is your power suddenly goes off as mentioned over here. Okay, let me just mark as mentioned over here. Suppose you hold a ticket which has the lottery number of these, you have these number on your lottery. Okay, and you turned on the TV to watch the result, but what you could see was only one number you could see which was being announced, and then suddenly power goes off. Okay, now what do you think is the probability of you winning the lottery? Is it better than before when you were not knowing that, okay, there may be a chance that I may match some number or 15 which I am already having, that is being announced? So would the probability increase or decrease? Just think about that. First case, when you are not knowing, okay, what exactly is going to be the numbers which will be announced. Second is, you know, one of the number being announced is 15, which you already have. Then you are having some probability of winning. So definitely you'll be having some, higher probability of winning. So how do you calculate that? That is the scenario over here. Whenever you are having such kind of problems, when you wanted to calculate some, chances of occurrence, or likelihood of something happening, and then you suddenly get to know, okay, that already this information is given to you, then you get more clarity that, okay, there may be more chances of something happening. Let me give you just another example over here. Suppose one of, there are five friends who are making a, plan for a trip. Okay, they are visiting some place, and suddenly one of the friend asked it, okay, where are we going? Then the other person may not be telling the exact place where they are going, but he may be giving some hint, like, okay, the person may ask, is it a hill station or a beach, or have we gone there earlier or not? So by asking these kind of question, by having these kind of information, we decrease what our sample space, and that's how we increase the probability of getting correct answer. I hope you are getting this idea. It happens a number of times in the household, in the home as well. Whenever mother asks for something, she keep on asking something, and then she get to know, okay, this is the thing which, my son or my child, basically my daughter, is hiding from me. Okay, so this is the scenario over here with respect to the conditional probability. We get some information, and based on that information, we finally get some better chances of occurrence. Okay, so we'll see such kind of problems. How do we solve these? So here is another motivation. Most of the people may not be knowing him. Okay, so this is screenshot from one of the show which was like Khulja Simpson, and this is like based on one of the older show, Monty Hall's Problem, over where this is a stuff like, okay, there are three gates, and behind each of the gate there is something. So behind one of the gate there is a car, okay, and behind other two there is something else, like there may be good or something else. So then it is being asked that, okay, you are told that you have to choose one door, and then you'll be having some winning probability. Winning of what? Winning of a car. Okay, you will be having some chances of getting a car, but then you don't know that which of the door has that car behind that. So then again there is this game which carries on further, in which you are given some hint, okay, that in one of the behind one of the gates or door there is something else. It will be shown to you. Now based on that particular information, that you were shown one of the gate that was opened, now you again have to decide that whatever decision I have taken for a door, that, okay, if I picked up that, okay, door number one, behind that there is a car, should I change my decision to switch to some other door or not? So something like this is, this is the conditional probability forms the basis of this thing, that if I get some new information, can I refine my probability, can I refine my chances of something happening? That is the concept of conditional probability. I hope you are getting this idea. Okay, so let's move further. So here's the definition of this thing. Okay, so let me just yeah, it's already here present. Okay, so consider two events A and B such that probability of B should not be zero. Of course, if I'm just putting it anything on denominator, you have to assume that, okay, it shouldn't be zero. This is like valid for any rational number. Okay, then conditional probability of A given B is P of A given B is mentioned as P of A intersection B divided by P of B. Okay, what is it? Probability of occurrence of A given something has already happened, something has already occurred. What is that? That is event B. Then what is going to be my new probability? The probability is going to be probability of occurring both the events together divided by probability of B event. That is what our conditional probability is. Okay, and this is very important point over here. If by any chance probability of B is zero, then conditional probability PA of given B is undefined. This is important over here. Okay, now if I think about, see over here, there is a diagram to just give you a better uh, visual idea about what is exactly happening. So see over here. So P A intersection B is this thing we already know. And if I talk about this P A given B, then what is going to be my probability? It is P of A intersection B divided by P of B, already mentioned. Okay, so there is a thing that why we are not considering A completely. Why am I not talking about this complete portion? Why is it so? Why am I not considering this? Let's just talk about that. So, like, if we go by some kind of intuition, we know kind of B event has already occurred. Kind of B event has already occurred. And if I talk about because B has occurred, what are the chances of my A event taking place? What are the chances of my A event taking place? So if I just break it down, like A can be written as simply A, let me write it as this thing, plus A intersection B. I can just break this part into two parts. One is this intersection part I'm having, and one other is this part, where only A is there, where only A is there. And this is the A intersection B. If I just break it up, there is no component of B in this area. There is no overlapping with B in this area. Okay. So if I say B has occurred, so that would not be having any effect for this part. That would not be having any effect on this part. So if I say that B has occurred, and if I want to talk about A, then this area should not be the part of my consideration for sure, because this was not having any overlapping with my B area. So what must be the area, or what must be the region I must be concerned about? The common region I'm having. That means this part. Okay, let me just repeat again. So when I had B event which has already occurred, in that case, I will always be having this thing that why am I not considering the complete A region? Okay, the reason being, what I wanted to calculate conditional probability. So if I know there is some extra information with me, so with that extra information, what I can conclude further. So if I want to conclude for A with the information that B has taken place, shall I be considering this part? No, because B was not playing any role for this particular area. For this particular area, I hope you are getting this thing. For this particular area, B was not playing any role. So over here, there is the chance. Okay, so that's why we consider the common region, and then we talk about, okay, out of total area for B, or out of total probability of occurrence of B, out of that, what are the chances of B, sorry, what are the chances of A also occurring in that area, or A also occurring for that particular consideration. I hope this idea is clear over here, that why we are concerned with common part A intersection B, not A minus B, or just only A, just only A. Why we are not talking about that? Okay, I hope this exact idea is clear to you guys. Okay, let's move further to get a better understanding. Okay, you'll get some more better visual idea over here. Okay, see over here. So intuitively, if I talk about, see what we used to write earlier, if I just tell you something like this, okay, that, okay, if I say simply my P of A is what? It is probability, or basically, if you remember, we have talked in terms of length, area, measure, okay, something like this we have already seen. So if I say that A is my set, okay, let's just consider that, then I'll be writing in basic form like this. In basic form, it will be written like this. A is my event. A is my event, that will be a set. So the number of elements present within that set divided by number of elements present in my sample space. We have already seen this definition. Clearly, we have learned all that. Okay. And if I talk about probability of B, what is that? That is, again, you know this. Okay. So when I say probability of A given B, what is that? That is nothing but probability of A intersection B divided by probability of B. So I can write it further like this. So number of elements in A intersection B divided by, for probability of A intersection B, it is going to be something like this. And if I write it as, like usual way, how do I normally write it? So what do I get? I'm getting something like this. So what kind of indication it is giving me? That my overall sample space has been reduced. You just see this thing, my overall sample space has been reduced. So it is a kind of way that my, occurrence of something, if the chances of occurrence of something is increasing, because whenever your denominator decreases, what happens? Your overall fraction increases. Let me repeat once again. Whenever in a fraction your denominator decreases, your overall fraction increases. So it is a kind of way that if I'm, just calculating conditional probability, in that case I'm reducing my sample space and overall probability is getting increased because I'm having some kind of extra information, provided there is some kind of overlap or some kind of relation between A and B. Okay, that is important. We will be discussing about that very soon, when we'll be discussing, the independent events with respect to that. Okay, we'll be discussing that in detail, need not worry. But I hope the idea over here is clear. Intuitively it is as if the sample space is now reduced to B because we are given the information that B has occurred. Okay, so this is the first point. Let me talk about the second point now. So here is a thing which is being used in, machine learning a lot. It is like causal inference. That can I conclude that one event leads to another event? Can I say one event leads to another event? So let's say if something like this is given, this may be asked in kind of, MSQ question or true false question. Basically, yeah, like which of the statement is correct, something like that. Okay, so if it has been given to you that P of A given B is greater than probability of only A. Okay, let me just write it again, it's not clear. Something like this is there, that P of A given B is greater than P of A. So can I conclude that because of B, A is taking place, B is increasing the chance of A happening because A was not taking place on its own. So B is a kind of, giving it a boost that, okay, because of B, the chances of A occurring is increasing. Can I say that? The answer is no. The answer is no. We'll find it out soon, that how we can say that. Okay, why do we say that? We'll just find it out. So see over here, I can break it down like this. P of AB, I'm just writing A intersection B as AB. What I can write it for this, this can be written like this. The P A given B can be written as P of AB divided by P of B, which is greater than P of A. If I just change the, this denominator, I just, change these places, what I get, and because these are positive quantities, I can surely, change these without affecting my inequality. So what I'll get P of AB by P of A, P of B, and I can write it as what? P of B given A, which is greater than what? P of B. So see, if I'm saying something like this, that okay, if this means, then I was saying B causes A, then should I say that A causes B now? The answer is no, because it was the same inequality. I cannot say, because how can both the things be true? Okay, and I use the same inequality to, come up to this point. Though there are different probability methods which we can use for causal inference. Causal inference means, can we say that this event causes another event? Okay, so over here I cannot say this directly. Okay, just remember this part. This may be important, this may be asked directly. I hope up to this point the idea is clear, that how we can, derive this thing, and how we can say that okay, there is no causal inference which I can, use with the help of conditional probability. Okay, now conditioning on multiple events, what does it mean by when we say that okay, there are multiple events on which a probability is being conditioned? So it is like simple. Earlier we were using only one event to be conditioned on. Now we are saying there are two events on which we are conditioning. So P of A given B comma C. It can be further written as P of A given, let me write it as BC. Okay, so that it doesn't confuse you much. B comma C means the intersection portion. Both the things are happening all together. So I can write it as BC. So what I can write it further, it is going to be, intersection of all divided by probability of BC. So I can write it as like this, simple stuff. Okay, and then you further know how you can, deal with these provided the information given to you. So this is probability of A intersection B intersection C, and this is probability of B intersection C. I hope the idea is clear. Okay, now come the last point, which is important. If probability of B is 0 greater than 0, which is like important whenever I want to talk about probability of A given B, we have already discussed it, because if probability of B becomes 0, then my conditional probability will be undefined in that case. So we have already seen these axioms. Okay, what were these axioms? Let me just repeat over here. So these were for basic probability of an event. Now we are talking about probability of an event conditioned on some other event. So again, the conditional probability must also hold true. They must also satisfy these axioms. Now let me just write all those with respect to conditional probability over here. So let me write the first one. The first one says that probability of A is greater than equal to 0. That means it is always non-negative. Remember axiom number 1. Okay, axiom number 2, probability of sample space given B is going to be 1. And third was that if I have disjoint sets, then their union can be broken down into the sum of individual probabilities. That means probability of, if I say A union C, let's suppose, and say A and C were disjoint sets. Okay, disjoint means nothing in common in between them. Then it can be broken down like this. Probability of A given B, and we can prove this as well. There is no problem which must be there with respect to this. I can prove. Okay. Let me just tell you about this one. When you just open it up, probability of B is already greater than 0, and then there will be P of A intersection B, and we know already that any event whenever we having, so probability for that event must be greater than equal to 0. And so if I say something like this, this is already non-zero. We have already discussed about it, and so this must be positive only. This must also be greater than equal to 0. So overall this must be greater than equal to 0. If I talk about the proof of second, so you already know what would be the intersection of sample space and B. It is going to be B itself. It is going to be B itself, because if I talk about just sample space and this B, let's suppose this is B and this is sample space, what is going to be the intersection? It is going to be B itself. So it will be P of B divided by P of B, which is 1 only. I hope this is again clear. And if I talk about this one, so A and C must be disjoint. So if I just talk about that, you can just write that as P of A union C, and then intersection with B divided by B, and then you just need to use the formula for sets. What do you will get over here? You will get P of A intersection B union P of, it is going to be C of intersection B. Something like this you can write. And then P of B. So you already know, because A and C were disjoint, hence the intersection with B, their corresponding intersection with B will also be disjoint. So now you can break it into two parts. So these will become A intersection B by P of B and plus P of C intersection B divided by P of B. So like you'll get this thing. I hope the idea is clear. The conditional probability must also satisfy the axioms which must hold true for any probability, any kind of probability we are having. We have already seen that. Okay. So now we'll solve a few examples, and we have already seen one of the motivation example. So we'll solve this example only. Okay. So let me just okay, let's take any example. 1, 14, 15, 20. Okay, I'll just write some sample one. So I just remember one number, which is 15. 15 was there, which was common. I'll just repeat the question, need not worry about that. 20, 30, and let's say 24. Okay. So within this lottery example, what we had was that a person was already having these 6 numbers from the lottery. And to win the lottery, whenever the lottery results are announced, they'll be telling the 6 numbers. Those 6 numbers must match with these 6 numbers. Only then the person would be winning the lottery. So the thing was, when that person was, watching that result on TV, he could just listen about 15 number only. He didn't remember because he, turned on the TV at some random time, and what he could hear was only 15 number. He don't know that before that some number was announced or not, and just when they announced 15, his light turned off. Okay, there was some electricity connection which went off, so he couldn't listen further. So he has only one idea that 15 is one of the number for the lottery winner. 15 is the one of the number for lottery winner. What are the chances of person winning this lottery? What are the chances of this person winning the lottery? And we'll compare both the event. Okay, one, when he was not having this information that 15 number was announced, first case. Second case, when he know 15 number is being announced, then what is the probability? So let's just talk about the first case. First case, when he doesn't know that, okay, 15 was one of the number, what is the chance of winning? So let me just tell you that the numbers are from 1 to 30, and those are by without replacement. These numbers would be picked up without replacement. These 6 numbers would be picked up by each of the candidates who takes this lottery numbers. Okay, so if I just talk about what are the chances of winning, so there will be only one combination who will be winning. Okay, that is going to be just one random number combination of 6 numbers. Okay, so if I say that, okay, a person winning when he doesn't have any idea about what number can be there, so there is only going to be one pairing which he may have. Okay, and what are the total combinations possible? What are the total combinations possible out of 30? What are the ways you can create, just group 6 numbers out of 30? In how many ways you can group 6 numbers? Select 6 numbers. We have already seen this. So this was the probability of him winning earlier if he could not hear that 15 number is one of them which is being announced. Okay, I hope this idea is clear. Now if I say that he heard that 15 number is one of them, he has already heard that 15 number is one of them. Now what is the chances of him winning? So let's say, this one was, let's suppose this was the only, this is the event. Let me just talk about that the lottery number is this 1, 4, 15, 20, 30, 24. So this is going to be only one combination because there cannot be more than one winner who are having same combination. So one was the only chance for the first case. Now if I talk about the second case, when he know that 15 number is part of that, so again now B is the event that 15 is one of the number. A event is the lottery numbers are these 6 numbers, and B is that 15 is one of the number. So there can be any number, any 5 number can be present. 1, 2, 3, 4, 5. Any 5 number can be present, but one of them is 15. So this is B event. This is B event, and this is A event. So what is going to be your, winning probability? What is going to be your winning probability? It is going to be probability of A intersection B divided by probability of B. And what is probability of A intersection B? So, like 15 must be one of the number and he is already having. So probability of A intersection B is nothing but probability of A, which is what? Which is what? It is, so let me just write, probability of A is nothing but it is equal to probability of A intersection B. That is same over here. Okay. Now, what is the probability of B? What is the probability of B? That 15 is one of the number. What are the chances that 15 is one of the number? Now, I don't know about five other numbers. I don't know about five others number. Now, those five numbers can be anything apart from 15. Those five numbers can be anything apart from 15. So, what is the total number of ways I can have this? So, probability of B will be, what will be in the numerator? In how many ways I can form a six, I can select six numbers such that one of them is 15 for sure and others are different. So I know those numbers would be from 1 to 30, leaving 15 behind. So how many numbers I'm left with? 29 numbers, and out of that I have to select only 5 numbers because one number is already there. From 30 numbers I was already having 15, so I won't be considering that cannot come. So out of 29, only 5 numbers I'll pick up for B event because 15 is already present with me. And what will be in the denominator? It will be 36 because out of those 30 any 6 number pair can be there. So what is going to be my answer for this one? So it is this thing, 1 upon 30 C6 divided by 29 C5 30 C6. So this can be cancelled and the answer for this is going to be 1 upon 29 C5. So if you'll just calculate, you'll find there is a difference. This is higher than this. The probability of A occurring, A given B has occurred, is going to be higher than this. And you can see this clearly because what is this? If I talk about 36, so it is going to be something like this. 30 into 29 into 28 into 26 up to how many times? 1, 2, 3, 4, 26 and 25. And then over here it will be 6 into 5 into 4 into 3 into 2 into 1. Okay, and if I just open this up, 29C5, 29 will go, in the backward direction till 5 numbers are done, and in the numerator you'll be having 5, 4, 3, 2, 1. So this part is going to be common. This part is going to be common. So you can see 6 by 30 is the fraction which was, which makes this first probability and second probability different. 6 by 30 is different. So let me just write it in a proper way so that you can get this. What I can conclude from this, that probability of A only is nothing but it is 1 by, if I just cut it up, 1 upon 6, 5. 1 by 5 of probability of B A. So you can see this is higher, and then when I divide it by 5, I'll get the probability of only A. That if he was not knowing that 15 is one of the number, what would have been the probability of him winning? Okay, how am I getting this? So like P of A given B is 1 upon 29 C5 and probability of A only is 1 upon 30 C6. I have just opened it up and I could get this was 6 upon 30 which was there, and rest of the part is going to be same because 5 till 1 would be going and 29 till 25 would be going. So this was 1 upon 5. So I know this is what P of A given B, P of A given B, 1 by 5, P of A. So over here you can see the probability of A given B is higher than probability of A. Okay, so this was a basic idea. That's what we started with. Okay, so let's move on to the next question. Again, a good question, simple question over here. So consider throwing a die. Okay, we are throwing a die, and then A is getting a 3, B is getting an odd number. So you already know within event A there is only 3 present, and within B getting an odd number, that means 1, 3, 5, these are present. So just find out what is the probability of A given B. It is going to be, what is common of this? Just find out. So what is the probability of B occurring? There are three numbers within this, so it would be 3 by 6. Okay, 3 by 6. 6 is the total number we can have, and probability of B, like there are only three numbers present over here, 3 by 6. And what is A intersection B? A intersection B is going to be 3 only, so this is going to be 3 by 6. So what do we get? Yeah, so probability of A given B, correct, A given B, getting an odd number. I guess I'm making, yeah, it is going to be 1, sorry, it is 1. Okay, intersection we will have only one number, so 6 will get cancelled, we will have only 1 by 3. Okay, now what about P of B given A? If I say that I have got 3, now what is the probability of getting any odd number? The answer is 1. Should I calculate that? Because I already know that I have got a number 3. I have already got that information. Now out of that, if somebody asks me what is the probability that I got any odd number, the probability is 1, because I got 3, only one number was there, and that is odd. I already know, and we can calculate it numerically as well. Intuitively, I hope you have got that. Okay, so how do we calculate that? Again, same thing. One, probability of A, this is 1 by 6, this is 1 by 6, you get 1 only. I hope the idea is clear. Okay, I hope these questions are quite giving you a good learning over here. So this is the question which is being asked in your sample paper by IISc Bangalore, okay, in DA sample paper exam. So we'll solve this. First of all, we'll solve this one, the one present on the right side. We'll solve this first. Okay, we'll solve this first. So like the situation is same, so that's why I have taken both the questions all together. The thing is, we have flipped two coins, or we can say that we have flipped one coin twice. There are two things: either we can flip two coins at a time, or flipping one coin two times. Both the things are same. Okay, over here to get the result. So yeah, let's say that we have flipped coin twice, and then let's find out the conditional probability that both coin shows head. Given that first shows the head, I have to calculate the probability. We can use both the ways. Okay, we can find out something like this, as I already mentioned, that we can calculate P of A intersection B separately, then P of B separately, and then divide. We can do that, or we can simply reduce the sample space as well. That is also one of the way, as we have seen in the last one. So if I just talk about this, what is the overall sample space I'm having? So it is going to be something like this: tail, 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 head, head, tail, and head, head. So it is given that first shows a head, first one shows a head, first one shows a head. So these are the two possible outcomes for that. Now out of these, what is the probability of getting both the heads? What is the probability of getting both the heads? It is 1 by 2, because only one I am having. This is the only case out of two when I'm having both the heads. So the answer is 1 by 2. Okay, simple, intuitively we have solved, okay, by having a look at the sample space directly. Now let's find out the way we do this. Okay, let's just do that. Let's just calculate using that. So what do I need to write? So I already know my A event I'm talking about is head, head only, and my B event I'm talking about is that first one had already shown head. Okay, so there are two possibilities for that. And what is my sample space? My sample space is PD, HH, TH, HT. So you can calculate now what is PA intersection B. PA intersection B. There will be only one number which is common to this. So one event, one would be the size of the event, and what would be in the denominator? 4. What would be P of B? That is 2 by 4. And when we divide these, we get 1 by 2 using this method. Okay, I hope the idea is clear. Now we'll talk about this one, okay, which is the example given in our sample paper. So the same thing, now it is being asked, given at least one tail has been observed. It is being mentioned that one tail has been observed. Now probability of getting two tails, probability of getting two tails. So basically I am given that B is something like this. At least one tail has been there. So tail head, head tail, and tail tail. These become my event B. This is my event B. And if I talk about this, A event is tail tail, tail tail. So if you want to calculate directly, you can do that as well. And if you want to go by, using sample space as well, you can do that as well. So, like what is the ratio for this one and this one? Because you have to calculate B in A intersection B. What is going to be that? If you can just tell me this thing, that would be sufficient to calculate this. And you can use this method as well, okay, using sample space. You can just try that, you'll get the same answer. So A intersection B is going to be this one only. And what is the size of this? This is 1. And what about the size of B? That is 3. 1 by 3 is the answer. So B is the correct answer. I hope this is clear. Now we'll move on to the next question, which is the last question. This is very tricky. People do this question wrong most of the time. I do know. Okay. So just have a look at this carefully. There is a big learning within this question. Okay. Let's see. So it is being mentioned that suppose that the population of a certain city is 40% male. 40% male. Okay. So we know probability of male is 0.4. Okay, 60% are female. Probability of female is 0.6. Also 50% of the males and 30% of the females smoke. So what should I be writing over here? Should I be writing something like this as for smoke, or should I be writing something like this? Just think about this. Just think about this, okay? And similarly, should it be female intersection smoking, or given that I know there is a girl, then somebody smokes, that probability is given. So I must tell you, this is this thing which is given to you, that 50% of the male, 50% of the males smoke and 30% of the females smoke. That means out of any male, if you pick up, the smoking percentage is 50%, 0.5, and for this it is 0.3. Okay. In fact, if I talk about myself, when I haven't learned this concept enough, I used to do the same mistake. Okay. So this is a big learning over here. How does this thing comes out? Okay. This is not intersection. This is given. This is conditional probability you are having already. Okay, because this is not something like this is mentioned to you that student or people who smoke and are male is 0.5 or 50%. That is not being mentioned. This is said that 50% of the male smoke. That means given a person is male, there is a 50% chances that he smokes. Okay, I hope the idea is clear. Similarly, we have to find the probability that a smoker is male. Now, what this thing is asking? Find out the probability that a smoker is male. Again, is it asking something like this? This is M. Or is it asking something like this? Or is it asking something like this? Probability that a smoker is male. Listen to this carefully. We have to find out the probability that a smoker, there is a smoker, that a smoker is male. That means you have given that there is a smoker, and then you have to find out that that particular smoker is male. That means you have to calculate this probability. Nothing like this. This was already mentioned, so you may get confused because of all these things. You have to learn what is being told to you. Okay, so this is something which you need to calculate. Probability of smoker, sorry, probability that a smoker is male. Given a smoker is a male, you have to find out that probability. So how do you calculate that? So you already know the formula for this. What is this? Probability of M intersection, sorry, this is going to be probability of M intersection S divided by probability of smokers. Now there is an important point over here. Okay, so here something familiar to you I'll be using without even mentioning you, which I'll be telling you later on. See this. This is important over here. So just because you don't know, but you have another way of calculating this thing. You need to find out this. For that you need this thing, this value, and this value you don't know exactly. But there is another way you can find it out, which is what? Probability that out of if a person is male, how many are the chances that he's a smoker, and then if I can multiply by this thing. Because if you remember, I guess we haven't written it, but yeah, we can just write it over here clearly. So always remember, whenever you want to calculate probability of AB, you can write it as probability of A given B into probability of B. So you wanted MS now, so you can also write it as S given M into probability of male. Okay. Now similarly, what you can do is you can break your S. Just remember your first or second class when we started probability exactly. Over there we had a concept of disjoint set, partitions. We have already talked about that. So if I have a set like this, smoker, and I don't know the percentage, or I don't know the probability of finding out the smokers, what I can do is I can decompose it into different partitions by taking intersection with our different partition sets, subsets. And what are those? Because I know if this is the complete population, half it, not half exactly, but in the disjoint part I can divide it into male and female for sure. But for the smokers I don't know exactly, because there is another kind of hierarchy and percentage which is given to me. So what I'll do over here, I'll just break down this thing like this. Just have a look at this carefully, and what result you'll be getting would be Bayes theorem, okay, which we'll be seeing in the next conceptual session when we will be solving this. Okay, so what I have written is, if you just talk about this, M union F, that is male union female, would be my complete set of people. And if I take the intersection with S, the number of smokers, I'll get S only. So I can write it in this way. Now I can further break it down. What is P S given M? We already know P of S given M is 0.5. What is probability of being a male? 0.4. So this is the value I'm already having. Now what we need to do, we just need to solve this. So this can be solved like this. S intersection M union S intersection F. So just remember, we have already solved this kind of stuff. Now, because this is a union of disjoint sets, so I can break it down into the sum of individual probabilities. 0.5 into 0.4, and then probability of SM plus probability of SF. And how do we get these? How do we get these SM and SF value? As we got this over here, because this is also your probability of SM or MS. That means smoker intersection male. Over here, smoker intersection female. So this will be the same value, 0.5 into 0.4, and probability of a person being a smoker and a female as well would be your 0.3 into 0.6. And that's how you get the final answer for a smoker to be a male. For a smoker to be a male. I hope the idea is clear. Okay. So these were the simple questions we had, because on the conditional probability you won't be having very difficult problems. And if I talk about further, we will be again taking some problems. You can see these. This was also asked in your sample paper. We'll be solving it in the next session. This is another problem from your sample paper only, and this one, yeah, and this particular example. This is a good example to solve, to get a proper visualization example. Okay, So this we will be solving in the next session. Till then, take care, guys. I hope you have learned, you have got this idea. And if you have any doubt, please comment down in the video. If you have learned, good enough, if you have got the idea, give me a thumbs up on this video. Okay, guys. So bye bye. Take care. Thank you.